Sustainability is a terminology which is used very much, very broadly in everything, with the risk at the end to create some, let's say, some skepticism to
Professor, we cannot hear you.
I remember myself having okay. Cultural heritage is very sensitive to climate environmental pressures due to various let's say, reasons. And I remember myself discussing with people from culture and to have a very, very important. Can you hear me? Can you hear Maria?
Now, yes.
Okay, sorry, it was a problem with my mobile. Somebody called me mobile, just was an intervention. Sorry for it. I will switch off. So, this is the reason because we have discussed a lot of times and to find the opportunity to work with people from culture because we need to find very urgently some solutions, even combining some extreme, let's say, extreme for people working in the culture, extreme solutions like, for instance, integration of photovoltaics in cultural monuments, or to see how to integrate, for instance, wave converters in very close to hortensias, or things like that. So you have really a new field, which is very, very new and very, very urgent to provide solutions. And as we have already discussed from this fantastic presentation of Mrs. Christopher last time, museums and sites consume energy, materials, and of course, generate waste. Also, sustainability gives, let's say, the hope for long-term preservation, and also following some rules to support the future and for the next generations, and of course, global community which owns this monument. Technically, also the construction accounts very high of the global emissions, about 37%, according to UNEP globally. Also, any intervention, we know, also the people who work more intensively in interventions know very well that there is during this intervention there is a consumption of resources, materials, energy. The old practices used more eco-friendly sometimes materials, but these materials are not very durable during time. Time is really something we need to take into account. These monuments, and time is not only one generation, but it's for generations. So any intervention should take into account how long is the time for a monument. The other materials we use, and everybody knows that we use strong materials, but these materials have very high environmental footprint, and this is one of the main topics of this round of discussions. And also, at the end, heritage should find a balance between what is going on in culture and environment protection, which is not always very clear. All of this give us some opportunities for further development and development, and of course research and innovation. And in our school and also in our university, we consider that we have a lot of opportunities not only to develop new ideas, but to research and but also to discuss how can work together different disciplines. Some list of challenges, and each challenge give us a new opportunity for research, and for development, but also for some companies this opportunity. As concerns the environmental challenges, some issues is the relationship with the extreme temperatures and how the building and all the structural materials, any structural materials, not only the building, but also any material, infrastructure material in the city has a problem. The rising sea put an issue for coastal and island sites like Venice or our potential in Crete. Also, the stronger storms, which every year are more and more strong, lead to flooding and increase of erosion even in areas of kilometers away from coastal areas. And as concerns the social challenges, it's what we see around us. It's the tourism of pleasure and the risk of cities to become just theaters or Disneyland for tourists. From the viewpoint of economy, the cost of restoration is huge. Maintenance is very huge, so probably an optimization means a prioritization, ranking of alternative solutions. Funding is never enough, and also conservation and economy need a kind of balance, and this balance is not very clear. As concerns the technology, which is very important, especially for schools like in our university, is how to integrate modern materials in historic structures, to find some sustainable solutions in terms of energy in technology, for instance, in the operation or indoor museum and protection of pieces of art, the obsolescence of conservation techniques, and also like in our case, as we will see it in the following charts represented by Christos and Korodakis, if data gaps and methodological complexity in this analysis. Now it's the time. I will stop my presentation. I would like kindly to ask Christos to start presenting the ReSEL principles and also some examples of also have some results from our analysis. Thank you, Christos.
Thank you, Professor. So my name is Christos Korodakis, and I'm going to present briefly about the methodological aspect of LCA and some case studies. So starting off with what is life cycle assessment? It is a systematic method to evaluate the environmental impact of products, processes, or systems across their life cycle. It is standardized by the ISO 14044 standards. And they include basically four main steps. We got the goal and scope definition, meaning that we have to define what is being assessed at the first stage, the functional unit to refer the environmental impacts, and the system boundaries, meaning which perspective of the life cycle we are assessing, meaning we can assess only the production of the product. As a second step, we got the inventory analysis, which is about the collection of inventory data of materials, energy emissions, and waste. The third step is about the impact assessment, where we translate these inventory data we collected in step 2 into environmental impacts, such as global warming potential in kilograms of carbon dioxide equivalent emissions. And the most important step is the fourth one, which is about the interpretation, where we analyze the results, identify hotspots and limitations of the study, and draw conclusions based on our results. So an important part of LCA is defining the system boundaries. For example, a study might look from a gate-to-gate perspective, meaning that we are assessing only the production stage of a product. Then we have another aspect, which is the cradle gate. We are assessing the raw material extraction to the factory gate. A more all-around assessment is the cradle grave, where we assess the whole life cycle of a product from the raw material extraction to its use and the end of the life. And another perspective is the cradle to cradle aspect, where we, in case the product is repurposed as a raw material for another production, where we assess the life cycle, recycling the product as a new product. Regarding the impact assessment methods, widely used in the industry is ReSEL 2016, where we start with the inventory results and through specific characterization factors. These are converted to 18 midpoint impact categories like global warming, freshwater toxicity, marine eutrophication, mineral resources. And through specific damage pathways, these 18 midpoint impact categories can be aggregated into 3 endpoint areas of protection, namely damage to human health, damage to ecosystems, and damage to resource availability. So what LCA brings to heritage science? We have the environmental impact awareness, since it can help professionals to understand their environmental footprint of conservation materials and methods. It can provide informed decision-making by comparing different conservation strategies. We got the sustainable procurement and design, since it can support the selection of eco-friendly materials for exhibition and restoration. It can advance the policy and strategy development because the finding can shape sustainability policies. And it can provide a holistic conservation planning, since it can integrate it with other assessment methods like life cycle costing and social LCA to assess the heritage conservation, environmental, economic, and social dimensions. So you will ask, why apply LCA in heritage conservation? Conservation interventions involve materials, energy, and resources, which contributes to environmental footprint. Different conservation techniques have different environmental profiles, and LCA can provide a structured way to measure and compare these choices and help integrate sustainability into decision-making cultural values. And moving to some insight from the literature, there is a growing research interest in the field of heritage building conservation, with clear growth identified in sustainability-related studies since 2015. However, most research is concentrated in Europe, and sustainability topics were understudied until 2018. LCA is an emerging tool in the field of heritage conservation research, And the recent bibliometric review from the literature conducted in the last 20 years, containing keywords of historical, historic, or renovation, and LCA, resulted in 310 publications. The authors identified as gaps the lack of data on traditional materials, the difficulty of quantifying the cultural values into LCA, and the absence of standardized methods for this sector. And the sustainability assessment can be applied into 4 dimensions, namely the life cycle assessment, where we assess the environmental impacts, the life cycle costing, assessing the life cycle economic costs, the social LCA, assessing the social effects of a project or conservation technique, and the life cycle sustainability assessment, which integrates all the above dimensions. Here's another perspective of the growing research in this field. And moving to another proposed 9 principles for green heritage science. These they cover 3 dimensions basically, because the environmental aspect with minimal derivation, efficiency, and the use of safe and non-harmful materials. Because the social aspect, where we have the value-led science, the democratization of heritage science, and the engagement of diverse stakeholders. And the economic aspect, where the main principle is the future-proofing of the monument, the efficient use of resources, and the modeling simulations for improved management techniques. And together, these can define a holistic sustainability framework for heritage conservation. In these principles, LCA can directly support several of these, like the resource efficiency, where we can measure material and energy use, the promotion of non-harmful processes, since we are assessing their environmental impacts, and the future-proofing of heritage, since we can, through the prospective LCA, we can compare long-term scenarios. Moving to some case studies, starting off with comparative LCA of restoration materials to be used in a village in Saudi Arabia. The authors compared the traditional mortars like mud and limestone to modern like cement and concrete. As a functional unit, they assessed the 80 square meters surface area over a 100-year lifespan, and they assessed depending on the data they had under the cradle gate or a cradle grave perspective, under the impact categories of global warming potential, the acidification and eutrophication potential, water use, and ozone depletion potential. And the key findings include that for the traditional materials like mud and limestone, there was lower embodied carbon dioxide equivalent emissions, but these materials require frequent replacement and maintenance. In comparison, the modern materials might be more durable but had a higher footprint. On the left, there is a contribution graph where we can see the contribution of each product in the life cycle and at which stage. Whether for the cement is during its production stage. Here are the total global warming potential values for the 5 materials, and these are for the mud is these results were as a result from for the frequent replacements. It requires about 5 to 10 years frequent in frequency. In comparison for the other materials, it's due to its nature and the transportation processes, because these materials are kind of heavy. Moving to another study regarding the stone consolidants, authors compared the different materials used to consolidate weather carbonated substrates, namely marble, limestone, and lime mortar. And they assessed 4 alternative consolidant materials, DAP, nanolimes, ethylic silicate, and acrylic resin. As a functional unit, the authors assessed the one square meter of treated substrate under the Crete perspective, and they assessed impact categories of global warming, resource depletion, photochemical ozone formation, human toxicity, acidification, and eutrophication potential. The key findings for each consolidant include for the DAP, across these categories, they were the lowest among the consolidants assessed. However, it had a high effect in human toxicity, acidification potential, and eutrophication potential due to ammonia emissions. Regarding the nanolimes, it had low impact across most categories. However, the main hotspots was the solvent use, which drove the photochemical ozone formation. And regarding the phthalic silicate and acrylic resin, performance varied by the substrate. And as a main hotspot was the solvent used for these products. The implication is that there was no single best consolidant, since trade-off depended on substrate and context. And as a key takeaway message, LCA can support more informed multi-criteria decisions for conservation practices and methods. Regarding the functional unit, I forgot to mention is that the authors assessed the practice of panel refusal, and they applied the material until the substrates could not uptake anymore. Another life cycle assessment of another aspect of adaptive reuse of historic building. Authors compared the concept of adaptive reuse of a building compared to demolition and new construction, assessing the building gross floor area of 1 square meter over a lifespan of 50 years under the Crete perspective, including impact categories of global warming potential, acidification potential, eutrophication potential, and smog formation potential. The key findings of the authors was that the adaptive reuse reduced the global warming potential by up to 82%, smog potential by 51%, and acidification potential by 53%. And the major benefits were from conserving the embodied carbon in the existing structure, and these benefits were observed across all impact categories. Adaptive reuse is a sustainable strategy, can be a sustainable strategy for historic and heritage buildings, and support the principles of resource efficiency and future proofing, and it can offer quantitative evidence to inform planning and policy. Here is a contribution graph for the building envelope, and we observed that the authors observed that the most impact categories are due to the wall structures. And here are across the impact categories the reduction potential of reusing the building and retrofitting it instead of demolishing and constructing something new. And moving to the social aspect of adaptive reuse projects, the authors applied social LCA of an industrial heritage building in Sweden. This building was renovated in 2032 and was repurposed as office space and workshop space. And they assessed the social impact across the project life cycle and several stakeholder groups. As a functional unit was the one adaptive reuse of the building under a Crete perspective. And the social indicators assessed included the workers, the local community, the society, the users of the building, and the value chain actors. And the key findings were that the adaptive reuse delivered positive local social benefits like jobs, cultural continuity, and improved accessibility. Regarding the supply chain analysis, revealed risk in global material sourcing, such as labor condition and worker rights, and highlight the social trade-offs that are not captured in traditional environmental LCA. Adaptive reuse can strengthen the social sustainability case for conservation, and LCA, social LCA can complement environmental LCA and progress towards life cycle sustainability assessment frameworks. And these heritage projects can support multiple sustainable development goals. To wrap up, some key lessons of these studies, regarding the materials, traditional against modern, there are trade-offs between low embodied carbon and durability and maintenance needs. Regarding the treatments, consolidators show no perfect solution, since they depend on solvent use and emissions that can create hidden hotspots. At the building scale, adaptive reuse offer major environmental benefits compared to demolishing and rebuilding something new. Regarding the social dimensions, the use can also generate positive social impacts, but global supply chain can bring some risks. And therefore, LC can help reveal hidden trade-offs and provide quantitative evidence to support conservation choices. And as a key takeaway message, is that there is no single universal solution. A decision depends on the context, scale, and the cultural values we want to protect. So to conclude, heritage conservation is part of the sustainability challenge, since conservation consumes materials, energy, and resources. However, LCA can empower professionals to make informed and sustainable choices, since it supports environmental, economic, and cultural resilience. LCA can reveal trade-offs, and since there can not be a universal best choice, since it depends on the context, the durability, and the compatibility matter. And these case studies show that traditional against modern materials, consolidants, adaptive reuse, and social dimensions can all benefit from the life cycle thinking. However, challenges still remain, since there is a lack of standardized methods for the heritage protection, the limited heritage-specific data, and the difficulty of integrating cultural values into the life cycle assessment frameworks. So the future direction is to move towards an integrated life cycle sustainability assessment, the use of digital tools, and stronger links between the policy, practice, and research. In closing, I would like to mention that heritage conservation is not only about preserving the past, it's also about shaping a sustainable future. And a life cycle sustainability assessment framework would offer a practical tool to guide planning and support towards the transition of more sustainable and preservable heritage. Here are the references of the previous slides, and we would like to thank you for your attention.